Hello everybody and welcome back. If you've been following the thermal physics series of videos, then by now you will have seen that we have arrived at these four definitions of entropy. And they're all very different from one another. If you haven't seen those videos, it's a good idea if you want to catch up on how we arrive at all of these definitions before watching this one. And I have a playlist called What is Entropy, and I'll put a link to that in the description below. But just to recap very briefly, we first saw what I call the thermal definition of entropy, which was devised by Clausius. And that is in terms of heat transfer, dq, and temperature, T. And this relates to the original second law of thermodynamics, which says that essentially you can't transfer heat from a cold body to a hotter body in isolation. That is, unless you put some form of work or energy into the system, you never have heat moving from a cold body to a hot body. And that inspired this definition of entropy, which Clausius found. And then we looked at the Boltxmann definition of entropy. Now, this is the statistical definition of entropy, and this is related to omega. And what omega is, it's the number of microstates which are compatible with the system being in the macro state that we observe it to be at. So a microstate is every individual arrangement of atoms possible, and a macrostate is the value of the macroscopic variables. So if I have my system to be at some temperature, volume, and pressure, then omega is the number of individual arrangements of particles which my system could have, which each would give rise to that value of temperature, volume, and pressure. So the greater the number of compatible microstates, the greater the omega, the greater the entropy. And that's the statistical definition of entropy. We then, from the statistical definition, derived the Gibbs definition of entropy in terms of probabilities, where the greater the probability, P, of being in the ith state, the greater the Pi, then the greater the entropy. So as we maximize entropy in the Gibbs version, we are moving to the most probable state that our system can be in. Now, that's a very important definition. And then finally, we started from information theory. So an entire different branch of physics, not thermal physics or statistical physics, but information physics. And that's when we derived the Shannon entropy. And the Shannon entropy, we found, was equal to the average information content of our system. So when we find out something new about our system, the greater the surprise, the greater the information content of what we found out, then the greater the entropy. Now, at first, you'd have thought that this Shannon definition should be entirely separate to the thermal physics definitions because we started at a totally different place. But what we found is that this definition here is identical to the formula for the Gibbs entropy. If we set the Shannon constant k equal to the Boltzmann constant kb, and if we take this logarithm here to log to the base e, or ln, then it is literally identical. And that's incredibly surprising because we started from such different ways of thinking about things and in entirely different branches of physics, but we arrived at identical formulas. And also we've seen the second law of thermodynamics, which says that as we move forward in time, the change in entropy, delta S, is greater than or equal to 0. So entropy can either increase or stay the same, but we never ever see a fall in entropy. So this is what we've covered so far, but again, each one of these definitions kind of feels like it sits alone. So the question we're going to ask in this video is what sits behind all of this? What is this thing we call entropy, which takes all these different forms and is so fundamental in so many different ways? And it turns out that the thing which really links all of these different concepts together is uncertainty. So, the thermodynamic entropy, by which I mean these first three definitions of entropy up here, are all concerned with our uncertainty about a system based upon our limited knowledge of that system. So that can be a limited knowledge of some of the macroscopic properties of our system. We might not know exactly what the temperature, volume, or pressure of our system is, for example. But equally, we could know all of the macroscopic properties of our system, but still have a huge amount of ignorance about the precise microstate of our system, the precise arrangement of particles in our system. So what we do in thermodynamics and thermal entropy is we say that subject to the constraints on the system based upon what we actually know about it, then what we have to do is maximize the entropy in order to find out what state of affairs our system will tend towards. Now, let me give you an example of that. Let's say I have a box of water, and let's say that it's a thermally isolated box which doesn't change in size. So I'll say that T, V, and P are all fixed. The temperature, pressure, and volume are all fixed, right? So this is our system, and these are our constraints. So beforehand, if we had no information about the temperature, volume, and pressure, then the system could be in any one of capital N microstates, right? These are every single possible arrangement of atoms, and the number of different arrangements is equal to capital N. But then we measure the temperature, volume, and pressure, and when we do that, we can eliminate a load of these microstates, because a lot of these microstates will be associated with the system having, say, a much higher temperature, so we can get rid of all of them. So we go from capital N microstates to little n microstates, right? So this is what we know about our system, and from imposing these constraints from what we know about it, we know that there are now little n possible microstates associated with our system. And what I'm going to do with our system is I'm going to put a small amount of blue dye in the top left-hand corner there. And what we need to do is use the second law of thermodynamics, in that entropy always tends towards a maximum, to determine how our system will change over time as we move forward in t, time. So what does that look like? Well, if I have my box again here, when I come back to it at a much later time, the dye won't have stayed in this top corner of the box, but instead the dye will be much more evenly spread out. It'll be approximately evenly spread out throughout the entire box. So what is going on here? Well, the number of microstates associated with our initial state over here, I'm going to call M1. So these are every single arrangement of atoms where all the blue dye is in this top left-hand corner of our box, right? And then the number of microstates associated with the dye being much more evenly spread out, I'm going to call M2. And the important thing here is that M2 is much, much greater than M1. There are many, many, many more arrangements where the blue dye is roughly evenly spread out than there are where the blue dye is in this top left-hand corner. So M2 is much, much greater than M1. And so by Boltzmann's formulation of the second law, where entropy is related to omega, where omega is the number of microstates associated with each state, then as we maximize entropy, we move from this state 1 up here to this state 2 over here. And that's because the number of microstates associated with 2 is so much greater than the number of microstates associated with 1. But then, what else do we know? Well, if we say that any one individual arrangement of particles is just as likely as any other, then we can say that the probability of being in the first state, P1, is equal to the number of microstates associated with being in that first state, M1, divided by little n. And little n is the total number of microstates that our system could be in, subject to these constraints. And likewise, P2, the probability of being in state 2, is equal to the number of microstates associated with state 2, M2, over n. And because M2 is so much greater than M1, we have that P2, the probability of being in state 2, is much, much greater than the probability of being in state 1. And then this links back to our Gibbs entropy, our probabilistic entropy. As we maximize the Gibbs entropy, we move from state 1 to state 2. So that's the thermal entropies at play here. But this example also gives an insight into how the information content entropy, the Shannon entropy, is connected to this. Because if you remember from the video about Shannon entropy, we said that the Shannon entropy is equal to the average surprise when we find out something new about our system. Now, what does that mean? Well, if let's do it by an example, right? If there are if M1, the number of microstates associated with being in state 1, let's say, for simplicity's sake, that is 3, right? M1 is equal to 3. Then if someone were to come along and tell you exactly which microstate we are in, then that information is related to 1 over 3, right? Because we have like an equal probability of being in each state, so the information associated with finding out exactly which state we're in is a function of 1 over 3. Whereas, let's say that M2, let's say that there are a billion microstates associated with this here, right? And then if someone comes along and tells you exactly which microstate you're in when we're in state number 2, then the information associated with that is far, far greater than the information associated with this. Because here, we could only have been in one of 3 states to begin with, so we could make a pretty good guess already about which state we're in. And if someone tells us exactly which, that's not a whole great surprise, right? We were close to guessing that anyway. But if we could have been in 10 to the 9 states, then if someone tells us precisely which state we're in, we've got a lot more information out of that, because we really had no way of even being close to guessing what state we're in before. The probability of guessing which state we're in is vanishingly small. It's 1 over 10 to the 9. So that is why the average surprise is much, much greater with this system, because we have much less information about the precise arrangement of particles in this system compared to this system. So again, if we are maximizing the Shannon entropy, if we're maximizing the amount of surprise we're going to get when we find out something new about our system, then again we move from state 1 to state 2. But the other thing to say about the Shannon entropy is that it's the only definition here which isn't linked to physical systems, because all these thermal definitions of entropy, thermal, statistical, probabilistic, they were all linked to being to looking at physical systems of particles. Whereas this Shannon entropy has a much, much broader applicability, because this doesn't just apply to physical systems, but it applies to any kind of system where we have information or finding out something or surprise. And that is why that a lot of people think of this definition, the Shannon entropy, as the most fundamental definition of entropy, just because it has the broadest range of applicability. So that gives an idea as to how all these things come together, and what we're going to do now is look at one more example which really drives home how these are fundamentally connected. Right, so what I want you to do now is imagine that we have some computing device, which is this box, and this computing device is storing n bits of information, capital N bits of information, and each bit can be either 0 or 1, right? And this computer is connected to a thermal reservoir at temperature T. So what we want to do now is totally erase every single bit of information in this computer. And so beforehand, the computer can be recording information which might be 0, 1, 1, 1, 0, 0, 1, 1, so on, right? But we don't know what that string of information is, but we're going to erase all of that information, and the way we're going to do that is by resetting every single bit to 0. We could reset every single bit to 1, but it's the same thing. So this is what we have here. Now, to start with, the total number of microstates that the system could be in is equal to 2 to the n. So each bit can be 0 or 1, and since we have n bits, the total number of microstates is equal to 2 to the n. Now, I won't go into combinatorics too much, but let's just imagine we had 2 bits, then the number of states, well, so they could both be 0, or the first one could be 0, the second one 1, or you could have 1, 0, or 1, 1. So with 2 bits, the total number of states is 2 to the 2, which is equal to 4. And then if we were adding one more bit, then we could have a 0 in front of all of these, and then we could have a 1 in front of all of these, and then you would be doubling this, so it's 2 to the 3, which is equal to 8, and so on and so on. So that's why the total number of states our system can be in is 2 to the capital N. Now you might say, well, it can't be in 2 to the n states. It can only be in one state because it's got one specific string of data stored there. And that's all very well and good, but we don't know what that data stored is. If we did, we would have retrieved it from another computer which is storing that information, or our brain would be storing it. The whole point is that before we retrieve it, we have no idea what this information is, and so the total number of microstates our system can be in is 2 to the n. Whereas when we are in this state, where we've reset them all to 0, there's only one microstate that we can be in. So the change in microstates is equal to 2 to the n minus 1. But since n is absolutely massive, then this is roughly equal to 2 to the n. So that's what I'm going to assume the change in microstates is. So we then have, according to this definition of entropy from Boltxmann up here, or equally the definition of entropy according to Shannon, either way we work it through, that we have that the change of entropy, delta S, is equal to KB ln of 2 to the n, and then this is equal to n KB ln 2, because remember with logarithms we can bring the power out the front. So we've had a fall in entropy here equal to nkb ln 2. So for the total entropy of the universe to increase, so the entropy of this computer has fallen by an amount nkb ln 2 because we've gone from 2 to the n possible microstates to 1 possible microstate. So in order for the entropy of the universe not to decrease, we need to eject a certain amount of heat into this temperature reservoir. And, well, we know from Clausius that delta S is equal to delta Q over T. So we need to an eject amount of heat, delta Q, equal to T delta S. And since this is the drop in entropy, we need to eject an amount of heat equal to N KB T ln 2. So this is where the information theory definition of entropy becomes immediately apparent to be linked with the Boltxmann definition of entropy. And then in order for the second law of thermodynamics to hold, we need to bring in this thermal definition of entropy. So this is the amount of heat which our computer needs to eject into our temperature reservoir. And as a side note, this is why your computer ejects heat. Even with a perfectly efficient computer, the best batteries, the best wires, everything perfect, you will never have a computer that does not eject heat into the surroundings. Because if you ever delete information on your computer, you are reducing the entropy content of your computer. And in order for the second law of thermodynamics to hold, which it always does, your computer needs to eject heat into the surroundings in order to raise the entropy of the universe. So I just think it's such a beautiful thing to really link the information content definition with both the statistical and the thermal definitions of entropy. And I hope that gives you sort of a good idea of how this sort of uncertainty is running throughout all the systems right up to the scale of the universe. So that's sort of the main point about entropy that I wanted to get across, that entropy is all about uncertainty. If we had perfect information, if we had perfectly precise information about every single particle in our system, then none of these versions of entropy would be applicable at all. There would only be one microstate, so Boltxmann entropy would be 0. The probability of knowing which state we're in would be 1 because we know which state we're in, so the Gibbs entropy would be 0. There would be no average surprise when we find out what state we're in because we already know, so the Shannon entropy will be 0. Entropy is all about uncertainty. It's saying, given what we know about our system, how can we maximize the probability in order to determine where our system will end up in the future. And that can be a physical system, or thanks to Shannon, it can be a non-physical system. And that's why entropy is such a deep concept. Right, so that brings an end to the entropy part of this course in thermal physics. What we're going to do next is the next few videos will be quite mathsy. So if that's not your thing, feel free to skip them. But they will set the groundwork for when we come on to talk about statistical methods in general, and then we're going to use that to go into Boltxmann distributions and ultimately the partition function, and that's a really fundamental and beautiful bit of physics as well. So look forward to seeing you then.